Hi, I'm Katie Smith and I'm affiliated with the University of Miami.
And I'm Sue Schaffler. I'm with the National Center for Atmospheric Research in Boulder, Colorado.
And we're both part of the Advanced Whole Air Sampler, or AWAS team. And we have our cans in the belly pod of the ER2. So we have 32 cans which collect whole air samples in the upper troposphere, lower stratosphere.
The way we sample is we have a pump that pulls air in from the outside, and then we fill up each can. We fill up each can individually, and we have a system where we can actually sample from the ground. We can tell the sampler when to open a can and close it, which really helps with our sampling strategy, trying to get these plumes that are coming off that we're trying to look at from convective outflow. And so what we do with the canisters is then we send them back to the laboratory in Boulder at NCAR, and they're analyzed on a variety of, it's on an instrument that with a variety of detection systems in order to measure a whole suite of organic compounds. So you can...
So we've got long-lived things like CFCs, HCFCs, HFCs, then some of the shorter-lived compounds which are quite important for the DCOTS mission, like dichloromethane and chloroform. So those have a lifetime of less than 6 months. And also non-methane hydrocarbons, which we'll use for trying to identify emission sources and things like that. So the analytical instrumentation can measure down to like subparts per trillion mixing ratios.
Yeah, really sensitive instruments. It's pretty impressive, actually, what we can do these days. And the non-methane hydrocarbons are one of the key set of compounds that we're measuring where we're trying to identify where air masses come from. So for example, the non-methane hydrocarbon signature, so this would be like propane, ethane, those butane, those kinds of things. The signatures are different, whether they're coming from cities, whether they're coming from agricultural areas, or whether they're coming from oil and natural gas. And we've seen signatures from that in the upper troposphere from these storms. They're bringing it up and parking it up there in the upper troposphere, lower stratosphere. And so that's part of the whole purpose of DCOTS is like, okay, you're pumping all this junk up there, what happens to it? How does it affect the chemistry and the local chemistry, and where does it go? How long does it have an impact? So that's one of the key things that we're measuring. The other part is we're trying to understand just background stratosphere. That's where measuring the CFCs that Kate had talked about. These are all the freons, the things that are involved in ozone destruction in the stratosphere. So that's a key part of that element of DCOTS is the measurements that we're making for these compounds. Our group is actually the only one that measures these in the stratosphere like this. So again, originally based in Miami, now at NCAR, doing these kind of analysis.
Where are the CFCs that you're measuring coming from now?
It's more sort of like checking the long-term trends and making sure that the concentrations are still kind of decreasing over time. There are some very small releases of CFCs, but it's from and halons and things from very strict procedures like fire extinguishers and things like that. But there aren't really any big emission sources for those right now.
And part of it, yeah, because she's right. It's not like how it used to be, but there's also refrigerators and appliances that have been around forever that still have CFCs in them that are emitting CFCs. So that's where a lot of the current emissions are coming from. And there's also some, I think, low-level emissions that may come from countries that haven't had to ban them, but I don't think it's mostly emissions from existing CFCs.
So maybe in landfill or something, if you've got a fridge in sort of degassing.
Yeah, and some of the replacements for the CFC-12, HFC-134A is one of the things that's being used now instead of Freon 12. And we're monitoring that in the atmosphere as well. That's been going up ever since they started using it. So we've been monitoring that in the stratosphere as well. And that one is a pretty strong greenhouse gas. So, you know, it's kind of a, well, phase out CFCs with HCFCs, phase some of those out maybe with some of the HFCs. And then you find out, well, yeah, but they have kind of a problem with global warming, so maybe we need to do something with those. So the chemistry and the global warming piece have been kind of going hand in hand in terms of trying to figure out how can we find something that's going to work on the industry side and something that's going to work for the environment. Industry now has been working more closely with the science community, and the industry themselves have really good chemists in there that are working with the, you know, with the chemists that are at NOAA and the universities and stuff to really try and say, okay, we want to use this. It looks like it'll work for us. What will this do to the environment? So they actually have been working together.
So they, before I come out with something new, it's a kind of standard procedure then to check with scientists to say, do you think this will be okay?
They would certainly be checking with their own scientists. Standard procedure to check with everybody else. I don't think, he's laughing up there. I don't think I would say that. Yeah, not quite standard procedure yet. We would like for it to be, but yeah, not so much.
When we talk about like the whole air sample, it's literally like a grab sample of air. So the cans will be open from between like 30 seconds to like 3 minutes or so, depending on the altitude. And it's like a real kind of just grab of that. So we take it back and we're looking at about 50 different compounds. And some of them will be right down like sort of sub parts per trillion, but others, like the ethane, for example, might be in the parts per billion. And it's sort of, so yeah, we see like the composition of the air and the different levels of those concentrations in that one sample.
Yeah. Are they under a vacuum?
So currently, yes. Before we sample, we've evacuated the cans. We add a tiny bit of water just to passivate the surface, and that helps preserve the sample. But when the plane's up, you know, that's what the pump is for. It overpressurizes them to about 40 psi, so that, you know, we sort of minimize contamination. And then on the analytical instrument, that then sort of comes out it's about 8 psi in a sort of analysis sample from that.
And is that like something that's happening automatic, or does the pilot have to do something to make it start?
Well, we have a new program that we were using last year as a LabVIEW program designed by one of our colleagues, and it allows us to target the plumes in the real time. So we're monitoring on the MTS platform, the live stream of data coming down. So we can see like the water trace and the CO, and when we see something like that indicates that we're in a plume from one of these overshooting tops or something, then we can press a button and actually take a sample right then and there. So
all the pilot really has to do is turn the power on for us, and we have a fast sampling mode that they can flip a switch if for some reason we don't have communication. We have a program that's on the computer that it'll just take over. If we lose communication, it already knows what it's supposed to do, so it'll do that.
That kind of blows my mind, though. I mean, the thing's 70,000 feet in the air, and you can control your instrument that's in the belly of it.
Yeah,
yeah, it was pretty good.
It was pretty exciting for us. This is the first time we've been able to do that last year during this campaign. Pretty exciting. Yeah.
And it's been really useful because the DCOTS mission is like kind of really targeting those plumes, and so now we can like make sure that we're getting the samples in the right places rather than just relying on an automated program.
And we're sitting up in the ops center with the meteorologists as they're watching during the flight. So there's a lot of communication in terms of, okay, something's coming up here, let's take a look and take a can now. You know? It's like, okay, we got it.
That's awesome. Yeah. But it's so amazing that, I mean, this is a big project with a lot of different science teams and a lot of support teams. And it's amazing as us, as we come in, to be able to see that we never would have thought that many teams are working in collaboration to get different data and yet supporting data. all at the same time.
Yeah.
This is this rare? Or would I expect this?
Not
I
for
don't
the
know, it's my
airborne
first,
missions.
yeah.
No. This is how it works with the airborne missions. Whether it's NASA or NOAA or National Science Foundation, they all work together like this, and it's critical. You have to, because you have basic mission science that you're trying to go after, and you know what measurements you need in order to get that science, and then you have the logistics of the aircraft logistics, and then also just the flight planning, the meteorology, all of those logistics. So yeah, they all come together like that. It's pretty cool.
That's awesome.